So first up, I got a question for Sasha here. How do you do stochastic approximation in Mathematica?
Well, thank you. That's a good question, although it's a little vague. So stochastic approximation can be applied to a variety of problems, including optimization and numerical integration, all of that other stuff. So really, we don't have stochastic methods for optimization, although Jim would probably be better fit to say. But so I'll focus a little about stochastic approximation to n-integrate. So n-integrate does provide out of the box Monte Carlo ways to approximate n-integrate, and the reference page does mention here several options for n-integrate. So we support Monte Carlo, adaptive Monte Carlo, quasi-Monte Carlo, and so on. So these are available to perform a multivariate integration over large dimensions. So specifically, you could see that that's, on this toy example, it's rather fast. One thing to know about it is that as soon as, when you do a Monte Carlo, each time you hit it, you get a different answer, right? So this is not something that you must alarm you. Now, if we will use a symbolic nature of Mathematica and wait for a second to get that integrate value, integrate computed explicitly, we'll get this expression in radical, and we'll get 3 decimal digits. You see that exact value, so we sort of got the correct ballpark, but not the right value. And we can actually ask n-integrate to do these computations repeatedly and use histogram to plot a distribution of the values it obtains. And you see that they cluster around some mean, which is close to the true value, but they actually are stochastic and sort of resemble a normal distribution. Now, if we want to change all of the Monte Carlo methods here are actually performed using each of these variables being uniform. And if we want to change that and change a different distribution for random numbers, we have an n-expectation which supports a Monte Carlo method, and you can specify distributions of each particular variable. So here, for instance, we are computing the expected value of a special function over parameter u being uniformly distributed from 0 to pi, and the modulus parameter varying according to beta distribution. So that's I guess as best I can answer the question. Thank you, Dan.
Excellent. Thank you, Sasha. Another question that's come in is for Paratosh. For larger systems of ODE, can matrices or vectors be used next to indexed functions in dsolve?
Right, and the answer to that is yes, you can. So let me show you a small example that'll demonstrate this. So what I'll do is I'll generate a matrix, call it mat. I'll just take a 2 by 2 system here, but of course this can be extended to a very large system. So I've defined a matrix, and what I'll do now is I'll use dsolve x prime of t equal to mat, and now I'll use the dot product, and I'll say mat dot x of t. So this is a linear system, but of course you'll get the idea. And then I can specify an initial condition, which will now, instead of a scalar value, it will take on a vector. So in this case, I'll say 1, 2. And of course, I'll need my braces for correct syntax. So that's my differential equation with the initial conditions. I give my dependent variable, t goes from 0 to 1, and we'll just say solution. Okay. So there's my interpolating function. And if I do x at 0.5, for example, you'll see that instead of one value, it returns a vector. So all this is neatly packaged inside of dsolve for you to make use of matrix vector type of ODEs.
Excellent. Thank you, Paratosh.
Sure.
Next question we have is for Jim. Jim, how can we set a constraint for the dependent variable which dsolve is solving for?
Yeah, okay. So this is possible. When I saw it come up on the screen, I pulled an example right out of the documentation, in fact. So what you do is you want to give a dependent variable specification. So I took the questioner's example of a variable which we know is between 0 and 1. You say dependent variables to y of t 0 to 1, and this will actually stop the solver when 1 is reached. In this case, the solution was an exponential. So you can also actually have custom actions here. Like you can print stuff just by saying rule delayed on that. And let's say, here t equals, and then let's just print the value of t there. And you get the value of t at which we went out of bounds. So yeah, this is definitely possible.
Excellent. Great. Thank you, Jim.
Sure.
We've got time, I think, for 2 more questions. So the next question, I'm going to go back to Sasha here. Sasha, what is the maximum precision that Mathematica can give for pi?
Well, that's a very good question. So I have to admit, I cheated a little bit when I said that in extended precision computation in Mathematica, we can take an arbitrary number of digits. That's really not correct because it's always limited, and it's limited by amount of memory in particular. But first, I want to get to a juice of the question, say that the Mathematica uses Chudnovsky formula to evaluate pi, and that particular formula gains about 32 decimal digits per iteration. The formula is stated right here, and the Mathematica, of course, can evaluate that. So the formula gives 1 over pi, which is then inverted. So you can ascertain that it gains 32 decimal digits by trying to do a logarithm and get that number evaluated. So you see that the asymptotic term of the asymptotic sort of behavior of the term is e to a minus 32k. So that's this, and now I want to sort of actually go and show it in the action. So using this Chudnovsky formula, we sum using the asymptotically fast binary splitting method developed by Brent. So we can say compute, well, 10 to the 6, it's cached, so it's instantaneous. But 10 to the 7 points takes 22 seconds, and 10 to the 8 point takes 347 seconds. So when we take a real number and represent it internally, it is represented as a sequence of binary words. And the maximum number of such words is 2 to the 64 minus 1. So that's a maximum representable integer number. So the total number of binary digits is this. And the corresponding number of decimal points is approximately 3.5 by 10 to the 20. Now, by doing a simple experiment, setting precision of 1 to 10 to the 8, we would approximate that should take approximately 1.5 times 10 to 11 gigabytes of RAM, and that will, you really need to take a very powerful machine to do that. But Mathematica should be, internally is capable of carrying out evaluation of pi to that many digits of precision. So, thank you.
Excellent. Thank you, Sasha. And like I said, we have time for one more question. This question is for Paratosh. And the question is, can parametric and dsolve take win event?
Yes, that's a very good question, and the answer to that is yes. And just combining parametric and dsolve with win event, you can do fantastic stuff. Let me go back to my notebook, and let's come up with a synthetic example wherein this is demonstrated. So I'll set up a function from parametric and dsolve, and again I'll take something trivial but good enough to demonstrate what's going on. I'll take an initial condition. We'll set that to s. So s being my parameter. S goes from t to 0 to 1. I will put the when event now. And now I say when event x of t is, I don't know, 1.5 or 1.1. Then x of t, add, I don't know, 0.5 to it. Okay? And with that, I'll generate, let's introduce dsolve value here. Okay, so there you have a numerical function. And now what you can do is take nf, and we'll set the parameter to be 1. You get an interpolating function out of that. Let's put that in, plot. And you can see that right when we wanted it, as soon as it hit 1.1, I added a value of 0.5 to it, so then the solution, you basically get this beautiful jump, and with that you can basically build on this and do fantastic stuff. Yeah, so that's basically the answer. Short answer is yes.
Excellent. Well, thank you, Paratosh.